Today's subject is the molecular mechanisms of contraction in the heart, in the cardiac muscle. In all muscles, contraction is dependent on an increase in intracellular calcium. That's the key starting factor in all contractile processes. So it is the key process also in the cardiac muscle. The calcium concentration in the cell in general, not only in contractile cells, muscle cells, but in all cells, the basal concentration of calcium is very low. It's kept in the nanomolar range. It's a really low concentration compared to the extracellular concentration of calcium, which is in the millimolar range. So there's quite a bit of difference. To start a contraction, you need to increase the calcium, intracellular free calcium concentrations up to the micromolar range. So there must be a group of mechanisms that will allow the cell to increase its intracellular calcium to micromolar range and then reduce it down to the nanomolar range in order to cell to contract. And if the cell is a fast contracting cell, like a striated muscle cell, this increase and decrease in calcium, intracellular calcium, has to be performed in a very rapid way. There are two sources that calcium comes from to increase the intracellular concentration. And one is the extracellular fluid, which contains about 2 millimolar calcium. This is the concentration of calcium in plasma also. And the second source is the intracellular organelles called endoplasmic reticulums. They are actually called sarcoplasmic reticulum in the muscle cells, and they store calcium. So the calcium inside these organelles are quite high in the millimolar ranges, similar to the concentration of the extracellular calcium. However, there must be another set of mechanisms that will decrease the calcium back to resting levels in order to stop the contraction and initiate the relaxation. So what are the molecules that play a role in intracellular calcium increase? There are two main players. One is the L-type voltage-dependent calcium channels. Now we're talking about mainly about the muscle cells, the striated muscle cells, the cardiac and skeletal muscles. It's a little bit different in smooth muscle cells. So these mechanisms are basically more or less, with some small differences. The mechanism I'm going to talk about is basically applies to all striated muscles, the cardiac muscle and the skeletal muscle. The components that are taking part to increase the cytoplasmic calcium are two L-type voltage-dependent calcium channels. These are voltage-activated type of channels which are selected for calcium, and ryanodine receptor channels. Ryanodine receptor channels are ligand-gated type of channels, but they are intracellular ion channels, and their ligand is calcium. We'll talk about this in more detail later. And there's another set of components which decrease the calcium, intracellular calcium, and these are two pumps and one exchangers. The pumps are the SERCA and PMCA. SERCA is a sarcoplasmic endoplasmic reticulum calcium ATPase. It's an ATP-driven pump which pumps calcium. PMC is also an ATP-driven pump, but it also pumps calcium, but their locations are different. We'll talk about these later. And there's an exchanger, which is called the sodium calcium exchanger, which is not a pump, it's an exchanger. So it's a secondary active transporter system. The locations of these components are as follows. Actually, this is a schematic representation of the striated cells, the cardiac cells and the skeletal cells. There are small differences between these two types of muscles, but basically the layout is like this. There are endoplasmic sarcoplasmic reticulum, as it's called in muscle cells, and an invagination of the cellular membrane. They come together to form triads or diads. You have to look to the histology books about the difference between the skeletal muscles and the cardiac muscles. But when the T-tubule and an enlargement of the sarcoplasmic reticulum come together, it's given a certain name in histology. In skeletal muscles it's a triad, and in cardiac muscles it's called a dyad. And the sarcoplasmic reticulum part of this dyad or triad, there are ryanodine receptors, and on the T-tubule side of the dyad or triad, on the T-tubule membrane, which is part of the cellular membrane, is the L-type calcium channels. So they stay in very close proximity to each other. And there, the pumps and sodium calcium exchanger is located on the membranes of the sarcoplasmic reticulum is SERCA. SERCA is called sarcoplasmic endoplasmic reticulum calcium ATPase, and it pumps calcium into the sarcoplasmic reticulum, and PMCA is on the plasma membrane, and it pumps the calcium out to the intercellular fluid. And sodium calcium exchanger also transports the calcium from inside of the cells to the outside of the cell. The events that lead to calcium increase, intracellular calcium increase, and then to contraction is as follows. First, you need some action potential. Action potential is a rapid change, depolarization in the membrane, the mechanisms which we talked about earlier. This is the starting trigger. When membranes depolarize, this depolarizes the T-tubules also, because they are also a part of the cellular membrane, and L-type calcium channels, as they are voltage activated, they open and let in calcium from outside. Some calcium enters through L-type calcium channels into the cytoplasm, but this is not enough calcium to elicit or start a contraction. However, they play an important role. They bind to the ryanodine receptors, which are on the sarcoplasmic reticulum membrane, and in close proximity to the L-type calcium channels. The calcium binds to these receptors, ryanodine receptors, and ryanodine receptors, when they bound calcium from the cytoplasmic site, they activate and open, and they can permeate calcium ions. Calcium within the sarcoplasmic reticulum, which is high in concentration, goes through ryanodine receptors and flow into cytoplasm of the cell, which binds to certain proteins and induces the contraction directly. They do not use calmodulin or other intermediary calcium binding proteins. They bind directly to the contractile apparatus and directly activate a contraction, which is a faster way of doing it. In other muscle cells, like smooth muscle cells, it's a little bit different. It has more steps in between the calcium increase and contraction. There is an important caveat here. We have to address that too. The calcium that is released from the endoplasmic reticulum, or sarcoplasmic reticulum, we should call it. It activates the neighboring ryanodine receptors, which actually is a positive feedback effect, which is called calcium-induced calcium release, and it ensures that the calcium concentration in the muscle cell will be increased in an abrupt global way. Calcium release has to be terminated in order to relaxation to start. But as there is a positive feedback mechanism in place, you would expect that the end point this process goes is the release of all the stored calcium into the cytoplasm. I mean, the cytoplasmic and store concentration should be equal. But this is not the case, and there are some unknown mechanisms which limits the release of calcium from the intracellular storage. The release stops before all the calcium in the storage is released into the cytoplasm. After that, the pumps and sodium calcium exchanger kicks in, and they start to remove the calcium from the cytoplasm, and SERCA pumps it back into the sarcoplasmic reticulum, and PMCA pumps it to the outer extracellular medium, and sodium calcium exchanger also, using the driving force of sodium, carries the calcium to the extracellular solution. At the end, the calcium levels drops to resting levels, and the contractile mechanism, because the calcium concentration drops, relaxes, and also the muscle relaxes. This is, in very general terms, how the striated muscle contraction is initiated and the relaxation occurs.